Hello students, this lecture is about applying Ohm's law to parallel circuits. And our objectives are to be able to identify a parallel circuit based on how components are connected and to use Ohm's law to solve for components in a parallel circuit. So you should already be familiar with Ohm's law and also perhaps with series circuits. And in this lecture we'll be taking that knowledge and applying it to solving parallel circuits. So let's take a look at a parallel circuit. What I'd like you to do is, in your notes, copy this circuit diagram and ask yourself these questions. So what I'm saying is I've got a 5-volt battery right here. We know that current flows from positive to negative, so current is going to flow along this path. I've got a closed path to get to the negative, so it is a closed circuit. But my questions for you are, what do you think happens when the charges reach point A? Question number 2, do you think the current is the same or different through the two resistors, and why? And question number 3, do you think that voltage will be the same or different across the two resistors? And once again, I would like you to answer why. So pause the video and take a few minutes to answer these 3 questions in your notes. Okay, great. We will be returning to these questions later on in the lecture after we've had a chance to learn a little bit more about parallel circuits. So let's take a look at what a parallel circuit even is. It's a circuit which contains side-by-side components all directly connected to the battery. And this definition has a couple statements that are important. The first part is side-by-side. Just as if we were to draw parallel lines in math, parallel lines are lines that are right next to each other and they never meet. These are parallel horizontal lines. Here are parallel vertical lines. They're side-by-side, and they're never going to meet each other as long as they're in that row. It's similar to that. A parallel circuit, you'll notice, has the components side by side, right up next to each other. And that looks different than a series circuit. If you remember, a series circuit has components that are one after another in a row. So here's a series circuit where I would have one resistor right here and then another resistor, and electricity has to go first through the first resistor and then through the second resistor. It has to go through those components in series, one after another. So this is a series circuit. And notice the difference in a parallel circuit. There are actually multiple paths at the same time that current can flow in because the resistors are side by side. Notice or remember that a resistor could be anything. It could be a bulb, it could be any electrical component that uses, converts, or transfers energy from the circuit to somewhere else. Okay, so these resistors could represent anything. We're just using resistors because that's convenient for now. A couple of things about parallel circuits. Current flows through all available paths at the same time. So it's not like it goes down one and then the other, then the other. All available paths from positive to negative are used. So current is going to flow through this loop over here from positive to negative. Current is also at the same time going to flow through this second loop over here from positive to negative. And current is also going to flow through that third loop from positive to negative, all at the same time. So electric current wants to take any path it possibly can to get from positive to negative. In this case, there are 3 paths available to it. It will take all 3. Next statement about parallel circuits. Each branch in a parallel circuit is independent. Independent means it stands on its own. So that means that a change in one branch is not going to affect any of the other branches. For example, if I change the resistance in branch number 2 of this circuit, if I change the amount of resistance in R2, that is not going to affect the current down R1. It's not going to affect the current down R3. each of these paths behaves almost as if it were its own circuit. And in a way it is, because each way is its own path. It's kind of like its own circuit. Next important point about parallel circuits. The voltage drop across every component is the same and equal to the battery voltage. So let's take a look at what this means. If you'll remember from a series circuit, we noted that if we took the voltage difference across this first resistor and then we compared it to the voltage difference across this second resistor, those two may not necessarily be equal. I could have some sort of V1 and V2, and we decided that V1 plus V2 should equal the total voltage of the battery. That was for a series circuit. In this case, notice that the voltage drop across each of these resistors in the parallel circuit is going to be exactly the same as the battery voltage. Okay, they are all directly connected, positive to negative. So voltage drop across R1 is going to be whatever the battery voltage is. Voltage drop across R2 is going to be whatever the battery voltage is, and so on and so forth. No matter how many components I have connected in parallel, they are all going to have the same voltage drop as each other. And we can think about that in terms of the electron shuffle. When we were doing the electron shuffle in class, we represented electrons with people, and each of those people were carrying a certain number of energy cubes. And the number of energy cubes per electron or per charge in the circuit, the number that each person was carrying, we called that the voltage. If each person was carrying 3 volts or 3 units of energy up here, remember when they get back around to the negative side of the battery, they're not allowed to have any volts left. We have to be at 0 volts when we get back around to the negative side of the battery. So in each of these cases, 3 volts has to be dropped or given away by each charge as they go through the circuit. Okay, so it kind of makes sense that each path on a parallel circuit is going to have the same voltage and may have different current. So this is the opposite of a series circuit in a way. In a series circuit, the voltages could be different and the current was the same because there's only one path in a series circuit. Over here, there's only one path through a series circuit. You have to go through this path, and that's all the choice that the current has. So current is the same, voltages could be different. In a parallel circuit, there are multiple paths, so current could be different, but because they're all connected to the battery, the voltage has to be the same. Okay? A little bit of opposites there. So last point, the current through each component could be different, and it depends on the resistance. So whatever the resistance is in each path could change the current through that path. Okay, so let's try and put this together into some steps for solving a parallel circuit. So steps. Step number 1. We need to recognize that voltage drops across all the components are going to be the same, and they're equal to the battery voltage. So whatever the battery voltage is, that's going to be the same as the voltage drop across every single component because every component is connected directly to the battery in a parallel circuit. Step number 2, you can find the current through each path using Ohm's law for each path. So basically that's saying you're going to zoom in on each path, use Ohm's law, I equals V over R, for that path, and you'll be able to find the current for that path. And then step 3, we're going to put all the paths together. Because we know the current in each path, we can add them all up and get the total current in the circuit. Okay, let's try an example. Draw this circuit diagram in your notes. Let's write our knowns. I'm going to assume that this is a 12-volt battery connected to this circuit, and I have 3 resistances in this circuit. Resistance number 1 is going to be equal to 2 ohms. Resistance number 2 is going to be equal to 3 ohms. And resistance number 3 is going to be equal to 4 ohms. So I have 3 resistors, and remember resistors could be anything. Resistors can represent either a physical resistor, that tiny little thing that we saw in our photographs and in our circuits. It could represent a physical resistor, or it could represent any other component at all that uses or transfers electrical energy out of the circuit. Okay, so these could be bulbs, anything you want. And we have 3 different resistances. So let's follow our 3 steps to solving a parallel circuit. Step number 1 is recognizing that voltage drops across all the components are the same and equal to the battery voltage. So I can make a statement that voltage across resistor 1, if I were to put a multimeter here in volts mode and measure the voltage across that resistor, it's going to be equal to the voltage across number 2, which is equal to the voltage across path 3, and all of these are equal to the battery voltage, which in this case is 12 volts. So that's a gimme. That's free information that we have for a parallel circuit, which is pretty nice. We never have to solve for voltage in a parallel circuit because we already know what it is. Step number 2, we're going to solve for the current through each path using Ohm's law for each path. So let's zoom in right now just on path number 1. What I'm going to do is zoom in on just this path right here. Okay, so if I'm looking just at that path, I can write Ohm's law for path 1. Current through path 1, that's what the little 1 is for, is going to equal voltage across path 1 divided by the resistance of path 1. Okay, I can use Ohm's law for the whole circuit, or I can use Ohm's law for a particular path. Here, we're using Ohm's law for a particular path. I know the voltage across path number 1. It's 12 volts, just as it is for all the other paths. The resistance down path 1 is 2 ohms. So I'm going to put a 2 there. I divide 12 by 2, and I get a value of 6. The value doesn't mean anything until I put units on it, and I know the units of current are amps. So current through path 1 is 6 amps. I can do the same thing for path 2. Current through path 2 should be equal to the voltage across path 2 over the resistance of path 2. Once again, I can do Ohm's law for any part of a circuit that I want, either the whole circuit or any part or path through a circuit. So voltage across path 2 is also 12. Remember our statement that every path in a parallel circuit is connected directly to the battery. So all of this is connected directly to the battery. It has the plus voltage, and at the negative end all of these have 0 voltage because they're all directly connected side by side. So voltage across every component is 12 in this circuit. The resistance in path number 2 is 3 ohms. 12 divided by 3 is 4, and the units are amps. And by now this should be pretty straightforward. We see a pattern. Current through path 3 is equal to the voltage across path 3. Let me erase that. That looks a little bit messy. Voltage across path 3 divided by the resistance of path 3. And that's going to be 12 again. 12 volts across all paths. And resistance of path 3 is 4, which gives me a current through path 3 of 3 amps. Okay, notice that the current through each path is not equal. It's not equal. I've found that the current here is 6 amps, the current here is 4 amps, and the current here is 3 amps. And take a look at the pattern that we see. The greater the resistance of the path, the lower the current through that path, which kind of makes sense in a physical way. So think about it. If resistance is how much current is being resisted or made difficult to flow, Higher resistance means it's harder for current to flow. That means there's going to be less current through that path. The number should be lower. And that is in fact what we see. Another way of thinking about it is to zoom in on just the Ohm's law equation, I equals V over R. Because R is on the bottom of this fraction, it's in the denominator, making R bigger makes this whole fraction smaller. Making R bigger makes that whole fraction smaller, which means that if I is equal to that fraction, well, I is going to get smaller as well. So we see mathematically that works out too. The bigger the resistance, the smaller the current. On my last step, step number 3, is to find the total current in the circuit. And we're told that it's the sum of all the branch currents. This makes sense too. If you think about it, current is just flow of electrons. So if I have 6 amps of charge per second going through here, I have 4 amps charge per second going through here, and 3 charge per second going through this pathway. Well, where did they all come from? They all came from the battery. There's some total current here coming out of the battery that's equal to the sum of all the different branch currents. So I should be able to add that up pretty straightforwardly. I'm going to say I TOT, or I total, the total current, should be equal to I1 plus I2 plus I3. It's got to be equal to the sum of all the different branch currents, just by conservation of energy. So I1 was 6 amps, and then I2 was 4, and I3 was 3 amps. If I add that up, let's see, 6 and 4 is 10, 3 is 13. I have a total of 13 amps flowing out of the battery to be able to power this whole circuit. So this battery is operating at 12 volts, and there are 13 amps of current coming out of that battery, flowing through the 3 different resistors, and then coming back again into the battery. Okay, let's try another example. Here's another blank circuit. Please add this one to your notes as well. Example 2. And these are going to be our knowns. Remember, a diagram with labeled values that we know is the first step in solving any physics problem. Okay, I've got a battery here. I'm going to make this battery a 24-volt battery. And I'm going to change up the resistances this time. Resistor number 1 is going to have a resistance of 8 ohms. Resistor number 2 is going to have a resistance of, we'll make it 4 ohms. And resistor number 3 is going to have a resistance of 6 ohms. So your task is to follow the 3 steps for solving parallel circuits and see if you can solve this circuit. What is the current and voltage for each component? Pause the video, give it a shot. Okay, let's see how you did. Step number 1 in solving a parallel circuit was to recognize that the voltage across all components, in this case 1 equals 2 equals 3, they are all equal to the battery voltage. Okay, these are all directly connected to a 24-volt battery. The voltage drop, how much energy per charge is given away in each component, is 24 volts. Okay, step number 2 was to use Ohm's law for each path to solve for the current through each path. Current through path number 1 is going to be equal to the voltage drop across path 1 divided by the resistance of path 1. And I know that to be 24. The voltage is 24. The resistance in that first path, if I go back up to my knowns, is 8. 24 divided by 8 is 3. Units of current are amps. 3 amps of current are flowing through the first branch of the circuit. Current through path number 2 should be equal to the voltage across path number 2 divided by the resistance of path number 2. 24 volts again. Voltages are easy in a parallel circuit. They're all equal to the same value, which is the voltage of the battery. So 24 divided by the resistance of that circuit, which is 4 ohms. 24 divided by 4 is 6. Units of current are amps. There are 6 amps of current flowing through path number 2. And a quick check, if we want to check ourselves, we can see that the resistance of path 1, is 8 ohms. The resistance of path 2 is 4 ohms. It should be twice as difficult for current to go through path number 1 as it is to go through path number 2, because the resistance is twice as much. So I would expect that there would be only half the current flowing through path number 1 as there is through path number 2. And indeed, that is what we see. There's only 3 amps flowing through path number 1 and 6 amps flowing through path number 2, which has only half the resistance. So let's continue. We'll do the same thing for path number 3. Current through path 3 should be equal to the voltage across path number 3 divided by the resistance of path 3. 24 divided by resistance of path 3 is 6. 24 divided by 6 is 4. Units are amps. There are 4 amps of current that are flowing through path number 3 of the circuit. If I go back up to my diagram, I can label that. Over here I have 3 amps of current, I have 6 amps of current, and over here I have 4 amps of current flowing through these circuits. It's really easy to see how I could find the total current, because if there's 3 going through this path, 6 going through this path, and 4 going through that path per second, then I better have 3 plus 6 plus 4 going through this path over here, coming out of the battery, because that current had to come from somewhere. We can't just make up current, and this has to do with law of conservation of energy, conservation of charge. We can't just make things up. They have to come from somewhere. So let's add that all up. The total current through the circuit, or total current coming out of the battery, passing through the battery, has to be equal to the current through, or the sum of the currents through each of the paths. Okay, so 3 plus 6 plus 4 is once again 13 amps. So I've made 2 examples that happen to end up with the same total current. Total current will not always equal 13, but in both of these cases it has. And so whatever your currents are through each of the individual branches, they will add up to a total current through the circuit, which is total current through the battery. Okay, let's return to our questions that we started the lecture off with. What do you think happens when the charges reach point A? Do you think the current is the same or different through the 2 resistors, and why? Do you think that the voltage will be the same or different across the 2 resistors, or why? And now what I'd like you to do at the end of the lecture, now that we're at the end, so at the end of the lecture, how would you answer these questions now? What changed about your answers, and what knowledge, which in science class we're calling evidence, changed the claim you were making about each of these questions? Okay, so add these at the end of the lecture as a sort of wrap-up. Make that 2 words, wrap-up, so that you can think about what you've learned in this lecture and make sure that we consider all of its implications. Back to our objectives. You should be able to identify a parallel circuit based on how components are connected. So if I showed you a circuit that has components side by side, you would know that that is a parallel circuit. Then you should be able to use the 3-step method that we discussed to apply Ohm's law and solve for all components in a parallel circuit. Solve for all components means, can you find the voltage across each component Do you know the resistance of each component? And do you know the current through each component? You know all three of those variables for every single component. If you can do that, you're good. Thanks for listening.